Welcome back. This is Machine Learning lecture number 3. Today we will talk about how to turn machine learning problems into optimization problems. That is, we're going to turn the problem of finding a linear classifier on the basis of the training set into an optimization problem that can be solved in many ways. To this end, we will talk about what linear large margin classification is and introduce notions such as margin, loss, and regularization. Let's start by motivating why we would aim towards large margin classification. Here I have drawn 4 training examples, 2 positive, 2 negative points illustrated with red circles, as well as 3 candidate solutions, where the theta is also included as a vector here to indicate the positive side. We could rule out one of them immediately because it does not correctly classify the training examples. The perceptron algorithm could select either one of these remaining 2 solutions or any other solution that still correctly classifies the training examples. It has no way of biasing which correct solution it will select, and there are many possible correct answers in this case. However, we would favor the solution that somehow is drawn between the 2 sets of training examples, leaving lots of space on both sides before hitting the training examples. This is known as a large margin classifier. Let's motivate why this might be something that we want to have. Let's say that the test examples that we see in the future are noisy versions of the training examples. In that sense, all the examples that we see are cloud of points around each of the training examples that are labeled according to the corresponding training example. So all of these would be negatively labeled test points. We have such a cloud around each of the training example. You can see pictorially here that the large margin linear classifier still correctly classifies all of those test examples. In contrast, the classifier here that hugs the training example very closely actually starts misclassifying those noisy versions of training examples very quickly. So a large margin classifier in this sense is more robust against noise in the examples. Let's now see how we can turn the problem of finding such a large margin linear classifier into an optimization problem, and we do this progressively in stages. Here I have drawn another linear decision boundary with the corresponding theta, as well as 2 adjoining boundaries that we will call margin boundaries. We have a margin boundary on the negative side, and we have a margin boundary on the positive side. These boundaries are equidistant from the actual decision boundary. The goal here is now to use these margin boundaries essentially to define a fat decision boundary that we will still try to fit within the training examples. So we will push these margin boundaries apart that will force us to reorient and move the decision boundary into a place that carves out this large empty space between the 2 sets of examples. Now, there are 2 aspects to this problem when we cast this into an optimization problem. One is this favoring margin boundaries that are far apart from the decision boundaries. That's called a regularization term. The other one is a counterweight, that as we are pushing these margin boundaries apart, trying to still fit the decision boundary between the set of examples, we might start violating the preference that all the training examples are outside this fat boundary. They may go in within the fat boundary or even be misclassified. This counterbalance is quantified in terms of a loss function that we may incur on each of the examples that does not fit this ideal picture. These two together now define an objective function for selecting the parameters theta and theta naught. That's a balance between the loss, how examples fit within this ideal notion, and regularization, our preference towards large margin solutions. So we will formalize the objective function and then find parameters theta and theta naught that minimize this objective function. Let's see how we do that formally. The first thing that we must do is to define what exactly the margin boundaries are and how we can control them, how far they are from the decision boundary. Okay, remember that they are equidistant from the decision boundary. So let's look at now the decision boundary, the equation, and the linear function that is defined on the basis of. That linear function takes the value 0 at exactly on the decision boundary. And if we move in the direction of theta, that linear function, that is theta dot x plus theta naught, will start having more positive values. We can then define the margin boundary as the set of x's where this linear function takes the value 1 exactly. We can see that this new boundary, by equation of a line, is parallel to the decision boundary because there is no point x that can satisfy the two equations. The linear function cannot be 1 and 0 at the same time. There is no x for which that is true. As a result, the two lines do not cross. There isn't a point in common. Now, on the negative side, if we move against the parameter vector theta, the linear function starts taking more negative values. And we can define the negative margin boundary by setting this linear function value exactly to -1. As a result, we have two parallel boundaries. They are equidistant from the decision boundary. And we can now try to push these apart because the margin boundaries themselves are also defined by the parameters that we wish to optimize, the theta and theta naught. It remains to understand the distance that the margin boundaries lie from the decision boundary and how we can control it. To this end, let's write down the decision boundary again here. Okay. Now, so it is all x for fixed theta and theta naught that satisfy this equation. We can divide the equation by the norm, the magnitude of the parameter vector, the length of the parameter vector theta here, and it still defines the same decision boundary. Okay? So as a result, it is the norm of theta that's a free parameter that we have not yet used. It is a degree of freedom that gives the same decision boundary as a result. We can use this norm to push the margin boundaries apart. Let's see how that works intuitively and then more formally in a little bit. intuitively, if we look at this linear function again, as we move away from the decision boundary, then the value of the linear function increases at a rate that's related to the magnitude of the parameter vector theta. Okay? So the larger the magnitude of theta is, the faster that linear function then reaches the value -1 here. Okay? As a result, in terms of the distance from the decision boundary, the closer the margin boundary is to the decision boundary, the larger the value of norm of theta is. Okay? So the norm of theta does control the distance that the margin boundaries are drawn next to the decision boundary. And it is a degree of freedom that's available for us to use. So now when we select the parameters theta and theta naught, it defines the orientation of the decision boundary as well as where the margin boundaries are drawn. So now we have parameterized this large margin decision boundary. And we can now turn to defining what the resulting optimization problem would be. Let's now define a little bit more formally what that regularization term is that allows us to control how far the margin boundaries are from the decision boundary. So here I have a negatively labeled point exactly on the negative margin boundary. Let's quantify the distance that it lies from the decision boundary. We know that the magnitude of the linear function itself as we move away from the decision boundary increases at a rate related to the norm of theta. So if we divide by the norm, we get a measure of distance traveled from the decision boundary. In this case, however, the actual value is negative, exactly -1 on the negative margin boundary. So if we multiply that with the negative label of that point, we get a measure of distance that point lies from the decision boundary. Okay, so the margin boundaries are really 1 over norm of theta apart from the decision boundary. Okay, so this is called a signed distance. It is signed distance because it measures the distance of a point from the decision boundary, but also the side on which it lies. So if it lies on the correct side of the decision boundary, the distance is positive, but if we have a negatively labeled point here, the distance would actually be -1 over norm of theta. Okay, so now our regularization goal here is to maximize the distance that the margin boundaries are from the decision boundaries. This will be our regularization term. Okay. Now we can proceed to define the objective function itself for finding large margin decision boundaries. It has two components, as we've already seen. It has a loss and it has a regularization. We have talked about both. So let's quantify now what that loss actually is. We know that the linear prediction here, the sign of it, relates to how the example is classified. If we multiply that with the corresponding label, we get a positive value when the prediction agrees with the label. Okay, so we can call this argument agreement. Let's denote it by Z. Now, we also know that if the point lies exactly on the margin boundary, say for a positively labeled point, the linear prediction is 1, the label is 1, and the agreement value is exactly 1. If it lies on the correct side of the margin boundary, but beyond the margin boundaries, then the value of z, the agreement, will be greater than 1. So we can now define the laws of how much our preference to keep the points outside the margin boundaries is violated by saying that the loss is 0 if the agreement is greater than or equal to 1. And then start penalizing, giving loss values for any example that penetrates into the margin boundaries. We can, for Hind's loss, this penalty is 1 minus z if z here is less than 1. So this will be a positive value that increases as z decreases, the agreement decreases below 1. Now, the regularization, we've already seen that we wish to maximize fine values of theta and theta naught that increase 1 over the norm of parameter vector theta, because that is exactly the distance that the margin boundaries lie around the decision boundary. Maximizing that is the same as trying to minimize the norm of theta, the same as minimizing the squared norm of theta, and we can just, for prettiness, multiply that by 1/2, which will become clear later why we do that. All right, so we can regularize the solutions by trying to penalize large values of the norm of parameter vector theta squared. So now we have an objective function that guides our selection of parameter vector theta and theta naught. That objective function has the two parts. It has an average loss, where each loss term measures how much that example violates the margin boundary, defined according to the Hind's laws that we just discussed. The other term is the regularization term that tries to push the margin boundaries further and further apart. Now, our objective function, how we wish to guide the solution, is a balance between the two. And we set the balance by defining a new parameter called regularization parameter that simply weighs how these two terms should affect our solution. Regularization parameter here is always greater than 0. Okay? For large values of lambda, the regularization parameter, we will favor large margin solutions, but potentially at a cost of incurring some further loss as the margin boundaries push past the examples. If the regularization parameter is very small, we favor really correctly putting the examples outside the margin boundaries, potentially at a cost of keeping the margin boundaries closer to the decision boundary. Optimal value of theta and theta naught is obtained by minimizing this objective function. So we have turned the learning problem into an optimization problem. Let's look at now how we can illustrate how the objective function guides the selection of theta and theta naught. Ideally, we would change the values of theta and theta naught, draw a different decision boundary and adjoining margin boundaries, and evaluate the objective function, and then seeing how the minimum of the objective function is guided by the points as well as the regularization parameter. To make this illustration easier, I'm going to instead introduce additional points here and just evaluate what the loss is that the objective function would assign to those points. So here we have a point that lies exactly on the margin boundary. We know then how to evaluate the Hind's laws of such a point. It is positively labeled. The value of the linear function is exactly 1. So the agreement here is 1 times 1 or 1, and the corresponding hinge loss is exactly 0. So the points on the margin boundary and on the correct points that are on the correct side and beyond margin boundaries incurred no loss at all. Points that now go into the margin boundaries do start incurring loss. To evaluate what that value is, let's start by evaluating what it would be if the point lied exactly on the decision boundary. At the decision boundary, the hinge loss is the linear prediction times label as the argument, and in this case it will be 0, so it will be 1 minus 0 or 1. Okay. Now this loss is a linear function of how much the point violates the margin boundaries. So the value is 0 here, it's 1 as it reaches the decision boundary. So the loss of this point, hinge loss for this point, is then in between, which is exactly 1/2. Okay, it will be 1 as it reaches the decision boundary and larger beyond. Here we have a negatively labeled point. We already discussed points that lie exactly on the decision boundary incur hinge loss, which is exactly 1. Now a point that goes beyond the decision boundary to the wrong side of the decision boundary. So this negatively labeled point now lies on the positive margin boundary. So as we move here, it incurs hinge loss 0. Here the hinge loss is 1. And as we take an equidistant step further in the wrong direction, we get an hinge loss for this point, which is exactly 2. All right, and if we go even further, it will be greater than 2. All right, so now we've seen how the different points incur loss in the objective function and thereby would guide the minimizing values of theta and theta naught. We will talk about the solution more later on in terms of how the solution changes by changing the regularization parameter lambda. So things to know from this lecture is the general point that the learning problems are cast as optimization problems in terms of objective functions that guide the setting of the parameters that we are estimating. The objective functions are decomposed into 2 parts: average loss over the training examples and the regularization that guides the type of solution that we are after. In our case, how large of a margin we can achieve for the training parts. We talked about large margin linear classification and how it can be turned into an optimization problem. To this end, we had to define margin boundaries, the distance that they lie from the decision boundary, how this relates to the hinge loss that we defined over the training examples, and how the regularization pushes the margin boundaries apart. All of this together define then the objective function that guides how theta and theta naught are resolved as the minimizing values.